This is section 11.1, part A, comparing observed and expected counts, the Chi-Square Statistic. So in this activity, students were to get a small bag of M&Ms. Mars Incorporated, which is the headquarters in Virginia, makes milk chocolate candies. Here's what the company Consumer Affairs Department says about the color distribution of the candies. On average, the new mix of colors of M&Ms will contain 13% brown and red, 14% yellow, 16% green, 20% orange, and 24% blue. The purpose of this activity is to compare the color distribution of M&Ms in your individual bag with the advertised distribution. We want to see if there is enough evidence to dispute the company's claim. For the time being, assume that your bag is a random sample of M&Ms from a population of candies produced in a particular batch. So each student would open their bag and carefully count the M&Ms. Don't eat any until the teacher tells you to. And then in the table, you are going to fill in the information. So you would say how many you observed, how many you expected based on the percent. So you do observed minus expected. You would square that value, and then you would divide it by the expected amount. So Jerome did the M&Ms activity with his class. The one-way table below summarizes the data that Jerome's bag of M&M chocolate candies. In general, one-way tables display the distributions of a categorical variable for individuals in the sample. So in his bag, there were 60 M&Ms, 9 were blue, 8 were orange, 12 were green, 15 were yellow, 10 were red, and 6 were brown. The sample proportion of blue M&Ms would be p hat is equal to 9 over 60, which is 15%. Since the companies claim that 24% of all M&M milk chocolate candies are blue, Jerome might believe that something fishy is going on. We could use the one sample z-test for a proportion from chapter 9 to test the hypotheses that the null hypothesis is p equals 24% and the alternative is that it does not equal 24%, where p is the true population proportion of blue M&Ms. We could then perform additional significance tests for each of the remaining colors. Not only would this method be pretty inefficient, but it would also lead to the problem of multiple comparisons, which we'll discuss in section 11.2. More important, this approach wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much as the one claimed by the company as Jerome's bag does, which is taking all the colors into consideration at one time. For that, we need a new kind of significance test called the Chi-Square Goodness of Fit test. As with any test, we begin by stating hypotheses. The null hypothesis in a Chi-Square Goodness of Fit test should state a claim about the distribution of a single categorical variable in the population of interest. In the case of the M&Ms, the categorical variable we are measuring is color. The appropriate null hypothesis is the company's stated color distributions for M&M chocolate candies is correct. The alternative hypothesis in a Chi-Square Goodness of Fit test is that the categorical variable does not have the specified distribution for the M&Ms. Our alternative hypothesis would be that the company's stated color distribution for M&M candies is not correct. We could also write in our null hypothesis the percent that they gave us for each color, and the alternative hypothesis would be at least one of the p sub i's is incorrect, where p sub color is the true proportion of M&M milk chocolate candies of that color. Don't state the alternative hypothesis in a way that suggests all the proportions have to be wrong, just that at least one of them would be wrong. The idea of a Chi-Square Goodness of Fit test is that we compare the observed counts from our sample with the counts that would be expected if the null hypothesis were true. Remember, we always assume that the null hypothesis is true when performing a significance test. The more the observed count differs from the expected count, the more evidence we have against the null hypothesis. In general, the expected counts can be obtained by multiplying the proportion of the population distribution in each category by the sample size. So Jerome's bag of M&M milk chocolate candies contains 60 candies. Calculate the expected counts for each color. Show your work. On average, remember, the new mix of chocolate candies has 13% of each brown and red, 14% yellow, 16% green, 20% orange, and 24% blue. So to do this, you would take the percent. So if we look at brown first, we're going to take the percent that is brown, which is 13% written as a decimal. We're going to multiply that by the sample size, and we would expect to get 7.80 brown candies. Now we would do this for every single color, and that would tell us our expected number of candies of each color. To see if the data gives convincing evidence against the null hypothesis, we compare the observed counts from our sample with the expected counts, assuming that H sub 0 is true. If the observed counts are far from the expected counts, then that is evidence we were seeking. The table below gives the observed and the expected counts from Jerome's sample. So we observed 9 blue candies, but we expected there to be 14.4. And we also, like for the yellow, we observed 15, and we only expected there would have been 8.4 yellow candies. So below is a side-by-side bar graph comparing the observed and the expected counts. We see some fairly large differences between the observed and expected counts in several color categories. How likely is it that the difference this large or larger would occur just by chance in random sampling of size 60 from the population distribution claimed by Mars Incorporated? To answer this question, we calculate a statistic that measures how far apart the observed and expected counts are. The statistic we use to make the comparison is called the Chi-Square Statistic. To do this, you're going to take your observed data, your observed piece of information, minus the expected. We're going to square that. We'll divide it by the expected value, and we'll add all of those together for every color in the bag, and that will give us our chi-square. So the chi-square statistic is a measure of how far the observed counts are from the expected counts, and the formula is stated below, where the sum is over all possible values of the categorical variable. So the table shows the observed and expected counts for Jerome's random sample of 60 M&M milk chocolate candies. Calculate the chi-square statistic. So to do this, you are going to take for each one, so we start with blue, we're going to do our observed minus our expected, we're going to square that, and then we're going to divide it by the expected value. Plus, we'll go to orange, the observed minus the expected divided by that expected value. Plus, for green, the observed minus the expected squared divided by the expected. And you're going to do that for every single color. And when you get done, we're going to get a chi-square value of 10.180. Think of chi-square as the measure of the distance of the observed counts from the expected counts. Like any distance, it is always 0 or positive. It is 0 only when the observed counts are exactly equal to the expected counts. Large values of chi-square are strong evidence against the null hypothesis because they say that the observed counts are far from what we would expect for the null hypothesis were true. Small values of chi-square suggest the data are consistent with the null hypothesis. So the question is chi-square equal to 10.80 a large value? You know the drill. Compare the observed value of 10.80 against the sampling distribution that shows that chi-square would vary in repeated random samples if the null hypothesis were true. So let's check our understanding. So the Mars Incorporated reports that their M&M peanut chocolate candies are produced according to the following distributions. So 23% are each blue and orange, 15% are green and yellow, 12% are red and brown. Joey bought a bag of peanut chocolate M&Ms and counted the colors of the candy in this sample. State the appropriate hypotheses for testing the company's claim about the color distributions of peanut M&Ms. So, for our null hypothesis, we can just say that it meets what the company says, or we can state by the color. So we can say the null hypothesis is the probability of blue is 23%, probability of orange is 23%. We can do that for each color. The alternative hypothesis is that at least one of the piece of eyes is incorrect. Not that all of them are, but at least one is incorrect. Where piece of color is the true population proportion of M&M peanut chocolate candies of that color. Calculate the expected counts for each color, assuming the company's claim is true, and show your work. So the first thing you would have to do is you would add up the number of candies that were in his sample. And then you would take each color and see what percentage it should have been and multiply it by that value. So the total number of M&Ms in the sample was 46. So they said that 12% should be brown, so we'll do 0.12 times 46, and we do expect 5.52 brown candies. 12% are red, so again, 0.12 times 46, and you would do this for every color. Calculate the Chi-Square Statistic for Joey's sample. Show your work. So remember, this is going to be the observed minus the expected squared divided by the expected, and you're going to add these all together. So if we start with brown, we'll start with blue because our blue was the first one that we sampled. So if we look at the last one, we expect 10.58 blue ones. So we would do 12 divided by 10.58 squared divided by 10.58 plus, we would then go to orange. We would do the observed minus the expected squared over the expected. We would do it for each color, and we would end up with a chi-square value of 11.3724.